All right, so this is the last section of Chapter 3, and we're looking at now some word problems where we see exponential growth and decay in real-world situations. So these are the formulas that we're going to be using a lot, and the beginning part is just kind of what our result is, or the function is. A sub naught, that's the way we would read this, A sub naught is what we're starting with. So if we're talking about a fossil that's decaying, it's the initial amount of the fossil. Or if we're talking about money that is growing in an account, it would be the initial amount of money that we started with. K is the rate that we're going to be using, and K will either be positive or negative based on whether it's growing or decaying. And then T is the amount of time that we're looking at. E is the variable or the number E that we're used to working with. So if our K value is greater than 0, we're looking at a growth. If our K value is less than 0, it's decaying, so the amount is either increasing or decreasing. Now, we're going to be looking at some examples in your book, and rather than putting all of the words and diagrams in the notes here, I've written some important information. But let me show you the problem in your book. So it says modeling growth of U.S. population. So we're given a table on the side here, and we're looking at our population, and it says in the figure, or the figure shows the U.S. population in millions for 5 selected years from 1970 to 2007. In 1970, the U.S. population was 203.3 million, and by 2007, it had grown to 300.9 million. The first part is saying find an exponential growth function that models the data. So we want to write an equation for part A. And then part B says by which year will the U.S. population reach 315 million. So we'll use our equation in part A to then solve for what the population, or what year the population will reach 315 million. So let's look at what we have here. Our A naught, the population we're starting with, is 203.3 million. And eventually it's going to get to 300.9 million 37 years after the start. So notice here T is equal to 0. 1970, no years have passed yet. But by 2007, 37 years had passed. So that'll be T equals 37. And now what we're going to be doing is trying to find that constant K value. That's what we want to find here in order to write an equation. So 300.9 million is what ended up what the population ended up being in 2007. Our start population was 203.3 million. E to the K power, we don't know what K is, that's what we're solving for, and the time that passed was 37 years. Well, now we can just start working with this equation and using the tools that we have to solve for K. I can divide both sides by 203.3, so 300.9 over 203.3 equals E to the power of 37K. And then I can take the natural log of both sides, and I'll have natural log of 300.9 over 203.3 equals natural log of E is just 37K, and then dividing by 37 on both sides, K is equal to natural log of 300.9 over 203.3 over 37. And when we plug this into our calculator, we're going to get about 0.0106. So that's our K value. All right. So then the equation that we're wanting to write, that's what they asked us to do in part A, would be A equals 203.3 E to the power of 0.0106 T. Part B, they say, what year will the population equal 315 million? So they're telling us the population, we're plugging that in for A, and we're solving for what year T. Well, the process we're going to go through is going to be the same. We're going to divide by 203, take the natural log, and natural log of this side is just going to be 0.0106t, dividing by 0.0106, t equals natural log of 315 over 203.3 divided by 0.0106, and that equals 41.3 when we plug it in our calculator. Now, because we are working with a real-world problem, we need to think, does this answer make sense? What does this actually mean? Because the question said, by which year? Well, the year isn't 41.3. The year would be this many years after 1970. And that would be 2011, but it's not just 2011. It's got to be a little bit over 2011. So really, what we want is by 2012, we will actually hit that population. By the beginning of 2011, we won't have quite reached that population yet, so by 2012. And that's the year that we're talking about. All right, so let's go ahead and flip the page and move on to the next example here. Now we're going to be talking about half-life. And a lot of times these will be examples that have to do with fossils or things like that. So looking at our book, the problem that we're looking at says, let's see here. We're talking about carbon-14 dating of the Dead Sea Scrolls. So part A says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to the half of the original amount. So after 5,715 years, only half of the fossil is left. And then it asks us to write an exponential decay model. Then it says in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman, and the analysis indicated that the scroll wrappings contained 76% of their original carbon-14. So, if it contains 76% of the original carbon-14, we can estimate the age of the Dead Sea Scrolls. Now that's a lot of information. Let's go ahead and kind of break down what it's asking us to do and what they gave us. So, with this example, we said that the half-life is 5,715 years. We're still using the same formula to solve, and we don't know how much the original was. We don't know how much the original fossil or sample held of carbon-14, but we know that only half of it is left. So then A is going to be half of A naught. That means we can write half of A naught equals A naught e to the k, and we said it took 5,715 years to get to only half of it left. So now we can divide both sides by A naught, and those cancel out. And now we have 1/2 equals e to the k 5715 power. Well, we can take the natural log of both sides, and that e will go away, and we just have k times 5715. So then k is equal to natural log of 1/2 over 5,715. Plugging that into our calculator, we get k is negative 0.000121. This makes sense that it's negative because our fossil is decaying, so it would be a negative value. So writing the equation that they asked for, that would be A is equal to A naught, whatever the original amount is, e to the k, which is negative 0.000121 t power. Part B told us that there was 76% of the fossil's carbon-14 remaining. So what we're going to do here is whatever the original amount, we still don't know what that was. We don't know what the original amount was, but we do know that only 76% of it is left. So we can write 0.76 A naught. And it's asking how many years did it take for only 76% of it to be left, or how long ago really, or how old is the sample. So we can again cancel an A naught from both sides, take the natural log, the E will cancel out, and we can solve for T. So T is going to equal natural log of 0.76 over negative 0.000121. And plugging that in our calculator, we're going to get 2268.07. So rounding, we can say that in 1947, like the question said, the Dead Sea Scrolls were 2,268 years old. And that's our answer. And because I'm going to run out of time here, I'm going to go ahead and stop the video now, and we'll do part 2 to finish up this section.